Warm greetings to all. Foremost, I thank the conference committee for giving me the opportunity to present the paper in this conference. I am Yakavi, research scholar under the guidance of Dr. Mydeen Bibi, Assistant Professor, PG and Research Department of Mathematics, the Standard Fireworks Rajasthan College for Women, Sivahasi, Tamil Nadu, from India. Today I am going to present the paper on the topic IP domination number of graphs. Here, IP stands for isolate pendant. And the outline of the presentation is that motivation, definition, followed by an example, observation, and results for IP domination number and relationship between IP domination number and domination number and bounds for IP domination number and ends with conclusion and references. Motivated by the interesting concept isolate domination and pendant domination, I derived the new parameter IP domination. I found IP domination number for standard graphs, path wheel rated graphs, and also some special graphs. First, let us see the dominating set. A subset G of V is called a dominating set in G. If every vertex in V minus D is adjacent to at least one vertex in G, the minimum coordinate of all this dominating set is called the domination number of G and is denoted by gamma of G. Next, we move on to our new parameter IPD set. A dominating set I, proper subset of V of G, is said to be IP dominating set if the subgraph set satisfies two conditions. One is that the induced I has vertices with maximum degree 1, and the other is this, the vertices or in induced I must have at least one isolated vertex and one pendant vertex. Thus, the minimum cardinality of IPD set is called the IP domination number and is denoted by gamma 01 of G. Let us see this with one example. Here I am taking bull graph. For this graph, the dominating set I is equal to V1, V2, V3. In induced I have two pendant vertices and one isolate vertex. This satisfies is said to be IPD set, that is IP dominating set. Hence, IP domination number gamma 01 of G is equal to 3. According to the definition, here we have some observation. Every IP dominating set is a dominating set. We have gamma of G less than or equal to gamma 01 of G. From the above example, if we take the above example as example, IP domination number is 3 and for the same graph, domination number is 2. Thus, gamma of G less than or equal to gamma 01 of G. Following observation provide insights into the properties of graphs that affect the existence and construction of IPD set. The first is that IP domination number exists for simple graph of order at least 4. And if a graph G has universal vertex U, say then U doesn't belongs to IPD set. If any graph G has a vertex of degree n minus 1 and it is not a cut vertex, then IP domination number doesn't exist. Next, we move on to the results. The first result is that for path Pn of order n greater than or equal to 4, then gamma 01 of Pn is equal to 3 for n is equal to 4 and 2 plus upper ceiling of n minus 4 by 3 for n greater than or equal to 5. The result proved by two cases. The case 1 for n is equal to 4. Here we choose I is equal to V4, V2, V1. Or else we can also choose the set V1, V3, V4 also. Anyhow, the dominating set I satisfies the IP domination condition. Thus, the dominating set I is said to be IPD set. Hence, IP domination number of P4 is 3. Case 2 is for n greater than or equal to 5. We have three subcases. First subcase is for n congruent to 0 mod 3. We generally found the IP dominating set I, which satisfies the IP domination condition. Thus, I is the IPD set. Similarly, we found IPD set for n congruent to 1 mod 3 and n congruent to 2 mod 3. From all these subcases, we have P domination number of P is equal to 2 plus upper ceiling of n minus 4 by 3. The second result is for cycle Cn of order n greater or equal to 5. Then IP domination number of Cn is equal to 2 plus upper ceiling of n minus 4 by 3 for all n greater than or equal to 5. From the above results, we can easily observe that both path Pn and cycle Cn have same cardinality, but they have distinct IPD set. The third result is that complete graph Kn greater than or equal to 3, IP domination doesn't exist. For this graph, IP domination doesn't exist because induced graph of I doesn't have isolate vertex. Here I'm taking an example, K5, that is complete graph of 5 vertices. For dominating, we only have V1, any one of the vertices from 5 vertices, it is a dominating set. For our IP dominating set, suppose we have to choose V1 and V2, still the IP domination doesn't exist because induced I does not contain isolate vertex. From this, we conclude that every IPD set is a dominating set, but converse may not be true. K5 is one of the examples for these conditions. Next, we have the results for the special graphs. First, let us see the exact values for IP domination number for path related graph, that is comb graph, ladder graph, coconut tree graph, book graph, and fan graph. Next, see that IP domination number for V related graphs also I have to find exact values, that is Helm graph, flower graph, gear graph. Next, we found IP domination number for some other special graphs also, that is a banana tree graph, lollipop graph, friendship graph, and barbell graph. Coming results establish the relationship between IP domination number and a domination number for standard graphs and special graphs. First, let's see the standard graphs. For path Pn, IP domination number of Pn is equal to domination number of Pn if n is congruent to mod 3. Otherwise, the domination number is added with 1, we got isolate pendant domination number. For Cn, n greater equal to 5, the domination number equals the IP domination number if n congruent to 1 mod 3. Otherwise, if we add 1 with domination number, we have isolate pendant domination number of cycle Cn. Right? So next we saw the relationship for some other graphs, that is for any graph with G with no universal vertex, then gamma 01 of G equals gamma of G if G is isomorphic to H. Similarly, for any graph G without universal vertex, then IP domination number of G is equal to domination number if G is isomorphic to radar graph, comb graph, and banana tree graph. If domination number is added with number of vertices in the graph G equals the IP domination number of G. And also, if you add 1 with domination number, we have isolate pendant domination number. And also here we see it. Finally, we have the bounds for IP domination number. If G is a connected graph, then 3 less than or equal to gamma 01 of G less than n. Here, the lower bound is 3 and its upper bound is less than n. If upper bound is equal to n, the condition fails because our G is connected graph, so the IP condition fails here. So definitely the upper bound is less than n. If a graph G without isolated vertices, then gamma 01 of G is less than or equal to n minus 1. Equality holds if G is isomorphic to P4. If G has no isolate vertices, then gamma 01 of G is greater than or equal to m plus 2 by del plus 1, where m is the total number of vertices in the graph. Here also equality holds if denominator exactly divides numerator.
Sorry, ma'am. You have 2 minutes left. Can you please conclude your article?
Yes, sir. Almost the end of the
Thank you.
PPT, sir. This is my end of the presentation. So I conclude that this paper introduced the IP domination number for graphs. We determine exact values of gamma 0 of G for standard path related graph. Additionally, we established bounds for IP domination and relationship between IP domination and graph domination. For further investigation as to parameters planned for future papers. These are my references, and thank you.
Thanks a lot for your contribution, Ms. Yakavi. I'd like to welcome this panel's chair, Dr. Kannan. Dr. Kannan, do you have any questions from Ms. Yakavi? And also other members of the audience, do you have any questions? If you do, please share it with us in the comments. Dr. Kannan, Dr. Bibi, do you have any questions? Okay, so we've received the question. What is the
Sir,
definition? Yes.
yes, yes.
Yes, sir.
Ma'am, you defined very well Yagavi, ma'am. So may I ask only one question from the candidate?
Yes, ma'am. Yes, ma'am.
Okay.
May I, sir?
Yes, of course.
Kanan, sir?
Yes, of course.
Yes.
You may ask your question.
Ma'am, can you give any real life applications for your domination number parameter?
Yes, ma'am. In security purpose, we can use this, or others in education institutions, we can use this, ma'am.
Okay. Thank you, Ms. Yakavi. Does anyone else have any questions? No? Okay.